Greetings, Earthlings. Today, we are going to study discipline. No, I'm just kidding. This is a mallet, but pretend this is a hammer. So we'll use this in a little bit. So we're going to go over the inscribed angle theorem, the hammer returns. Let me give you guys a little bit of background, then we'll jump in. So the point of today is we are going to examine this little question, or rather the theorem, which states that if you have an angle which is called an inscribed angle because it's inside of the circle, on the circle, if this is x degrees right here, then this would be half the measure of this arc. In other words, if this is 2x, that would be x. So for example, this is 50 degrees, that would be 100 degrees. So that's the claim. That's going to give us a lot of mileage. So let's see what we can do with this. And before we jump in, I'm going to introduce some vocabulary. I'm not really big on vocabulary, but at the same time, it's a necessary evil just to get it out of the way, just like you have to learn your alphabet before you can write. So a few things. I may not even use all these terms, but hopefully this will help you guys in knowing the terminology. So there's subtend and then there's intercept. So this angle, this x degrees right here, is going to intercept this arc. So what that means is going to cut off. Just like you can intercept a package, you can intercept communications. So we have this arc, and think of these rays as cutting off that arc. So that's when we're referring to intercepting, that's usually you're intercepting an arc. So that arc BC would be intercepted by angle BAC. All right. Now, it goes in the other direction as well. So we have this angle BAC, that's this x degree angle, and this angle is subtended, that's the vocabulary term, by this arc. So the arc is intercepted, the angle is subtended. Anyway, that's just the terminology, so just so you guys know. All right, naming arcs. So I can refer to this arc as BC, but actually that's a little vague because this is arc BC, but so is this. So you might say this is the minor arc, and that's the major one because this one's larger. So usually, to avoid this kind of confusion, what we can do is tack on an extra point. So since we have this point A, if I say arc BAC, then that means I'm going from B to A to C, so that's definitely this arc. So if I can include an imaginary point D, let's say, and then if I said BDC, it would be completely unambiguous. I'm referring to this arc and not that arc. But I think for our purposes, when I say arc BC, I'm always referring to this one. All right, so that's a little bit about naming arcs. Then there's these other terms, you might have seen them or not, secant, tangent, and chord. Now secant also has a meaning in trigonometry. We're not referring to that sort of secant. So for our purposes, any line, so let's say there's a line cruising along, if it hits the circle in exactly one point, that would be called a tangent. A secant would be one of these. So let's say if we were to extend one of these lines, it's going to hit the circle in 2 points, as will this one, in 2 points. So these lines are called secants, and the segment of that line, so like, let's say AB, that's called a chord. So a chord just hits a circle in 2 spots. And AC is another chord. Now, what's a special chord? The diameter is a special chord because it goes right through the center, right? That's the largest chord you can make in a circle. So that's a little bit on definitions. Don't worry too much about those. All right. So, also, let's back up a little bit. I really want to stress, I know we're going to present this, and a lot of you just might want to know how do you do this inscribed angle theorem proof and stuff like that. But I want you guys to get more out of this video. Let's go back to our triangle idea. So we proved the area of a triangle, and we had different cases. We had our right angle, we had our acute, and obtuse. So in that case, pretend it's a hammer, we built a hammer. Now what was our hammer in that case? That was our right triangle. Why? Because it was easy, and we used it to prove the other cases. Because you could split this one, so it's kind of adding 2 right triangle cases. And in this case, you could do that, and we're kind of subtracting this large one and this small one. So by building our hammer, we can add, subtract, we can play with our hammer. All right, same idea we're gonna use the same idea here. First, a little bit, some things that we kind of must know before we can do anything. A central angle is exactly what it sounds like. It goes through the center. So notice this is on the circumference, this is on the perimeter of the circle, and this goes to the center. So when you have an angle that goes to the center, it's pretty straightforward. If this is x degrees, it corresponds to an x degree arc. So for example, if this is a 90-degree angle in the center, then this would be a quarter of the circle. The arc is also 90 degrees. We're going to use this. Without this, we can't do anything. So that's our kind of key point. All right. So now finally, let's get to the meat. How are we going to prove that if this is x, that's twice x? It seems pretty tricky because this is in the middle of nowhere, right? We have there's no knowledge that we can even come up with. So we have to build our hammer. Now what's going to give us a hint? It's this central angle. So if we had a central angle, it would be easy. But this is like out in outer space. We have to connect it to that point somehow. So moreover, let's ask ourselves, can we come up with a special case? We want to build our hammer. So maybe we can make one of these chords a special chord. Now what would be a special chord? See if you can come up with that. Well, why don't we start with one of these chords being the diameter, right? That's a special case because in general these can be anywhere. Now also, this is something that I used to get confused on, and many of you might have this question. If our diagram is not to your liking, you can always rotate the circle, right? So for example, you might think, well, what if this point is over here? So like if we take this diagram, let's say, and it's like this, that's your center. You might say, aha, that doesn't look like that. But we could just take this and rotate it so it looks like that. All right, so if this is x degrees, we want to figure out what that is, or vice versa. If that's 2x, we want to show that that's x. Now, here is our special case. Oops, misspelled special there. Okay. Why is this a special case again? Because this segment just happens to be the diameter. So how do we know to do that? Using our idea of building a hammer, we always try to start with something simple and make it a little more complicated gradually. Whether this is athletics, music, whatever, you don't want to start with the most complicated stuff. And that's the most complicated stuff. All right, so now we made this a special segment, but we're still confused. Now, we need a little bit of an insight. So what we're going to try to do is just add a little bit to our diagram. So what are we going to add? Well, what's a nice segment that might be connected to this? Let's add this. That's really the key. That's the key. All right. After we do this, after we add this, you guys might be stuck again. However, there's a very interesting thing that happens. What is this? This is a radius, right? So this is a radius. This is a radius. All three of these are radii. So that you might be like, duh. But what that means is if these two are the same, this is an isosceles triangle. That's something that I've missed on so many occasions. That's why I'm making such a point of it. You'd be surprised how hard these problems can get if you miss that insight. All right. Therefore, this is also x degrees because in an isosceles triangle, these sides are the same. The angles opposite them are the same as well. So, now, let's call this y for a second. We know that if this is y, according to this arc here is also y degrees. Now check this out. This is a straight line, so y plus whatever this angle is going to be 180. And the three angles here sum to 180 as well. So in other words, 2x plus whatever that is 180, and y plus whatever that is 180. So therefore the 2x must be the same as the y. Let me run that through again. Let's call this z. If y plus z is 180 and 2x plus z is 180, therefore the 2x must be contributing the same thing as the y. We can do this in equations, but I want you guys to have a little more intuitive feel for it. Alright, therefore this, and this is always true, not just in isosceles triangle, this exterior angle is always the sum of the opposite two angles. So what have we shown? We've shown that y is 2x. That's it. So that is our basic case. We've built our hammer. So in this special case where one of your sides here, one of your rays, is the diameter, we know this is going to be half of that arc. Alright, so now comes the fun part. Now we're going to use our hammer. So we have case 1. Now, the question is, what are all the possible cases? Where here, one of your sides is the diameter. What if your diameter is outside? So maybe you have something like this. So that would be the diameter over here. In other words, it's outside of this angle we care about. Or we can eat up the diameter. The diameter is inside, right? So those are all the possibilities. This side is either on the diameter, to the left of it, or to the right of it. All right, and by the way, like I said, we can rotate any other diagram into one of these where we're looking at it horizontally like this. Okay, so we're going to use the same logic over here. This is our hammer. Hammer. So in this case we know this is x degrees, that's 2x degrees. Let's go to this third case because it's probably the simplest. So that means we could split this into 2 cases. So this is A and that's B. I just don't have room for the degree sign, those are degrees, right? So this is A, this must be 2A. How do we know that? We're using our hammer. And this is B, that's 2B. So the combined angle is A plus B, and if you add these you get 2A plus 2B, which factors into twice that angle. So we've proven case 3. Case 2, I'm actually not going to prove. I'll leave as an exercise to you guys. But the idea is similar to this. So here's our hammer. Here we added things just like we added things here. And if you're stuck here, think about how you would prove this. Alright, I'll see you guys in the next video. If you're desperate and just want to know how to do it, feel free to ask me in the comments and I will post a solution in the comments. Oh, one more thing, forgot. There's Paul Lockhart, math professor. His famous work, A Mathematician's Lament. I highly recommend all of you read it. But for our purposes, a little bit of a fun fact from this. So now that we've proven this, like what's one of the more common ways this appears? If we have a circle, and this is the diameter, if we take a triangle where this third side is the diameter, it'll be 90 degrees. That's the claim. Now why is that? Because remember, we can use this fact, which will be that this angle is 1/2 of this arc. That's what that says. And since this is half the circle, the whole thing is 360 degrees. So half of it is 180. And what's half of 180? That would be 90. So no matter whether it's this triangle or this triangle, any one of these triangles, these are all right triangles, which is pretty cool. Like that may not be obvious. So that's one of my favorite applications. Now, in Paul Lockhart's Lament, he shows a very cool solution that one of his students came up with for showing this, and it's not going to involve this. So I just, for completeness and for fun, I thought it would be nice to see the approach there. So let's say we have this triangle, and again, what are we trying to show? We're trying to show that this angle is going to be 90 degrees. So here's the cool solution. Let's take this triangle and let's rotate it 180 degrees. So if you can just imagine flipping it, it will look like this. So because we've rotated it 180 degrees, these sides will be parallel. And you can intuitively convince yourself as well. And these sides will be parallel. Now that's still not a complete proof because this is all we've shown is that this will create a parallelogram. However, remember this is the diameter, and right here what we have will be, because remember we took this point and we moved it 180 degrees. So what does that mean? We've created another diameter. So that means that the two diagonals are the same. And if the two diagonals are the same, that means this is not just any parallelogram, it's a rectangle. So therefore this is 90 degrees. I thought that was a really cool proof. So hope you guys enjoyed that. Let me know in the comments if you have any questions or if you want me to prove that second case or anything, and I will see you guys in the next few videos. And don't forget, use your hammer.